There's an interesting physics puzzle that sparked some discussion on the physics memes subreddit a few days ago. I'll leave a link to this post in the description if you want to check out the meme, and I've recreated the puzzle on screen right here. The question was if these two mechanical systems behave differently. In particular, if the trajectory of the 10 kilo mass is any different in the two cases. I remember being led astray by a similar puzzle back in the days, and I think it's a great teaching opportunity. So before we begin discussing the puzzle, I would like to establish g equals 10 meter per second squared, such that a 5 kilogram mass is indeed accelerated by a force of 50 newtons. So let us now analyze the two systems. Each consists of a 10 kilogram block placed on a table with coefficient of friction equal to 0.2. Attached to that block is a string that is led around a pulley at the edge of the table. In case 1, a downward force of 50 Newton is applied to the string. In case 2, a 5 kilogram block is attached to the string instead. Earth's gravitational field is acting on that second block with a force of 50 Newton, and thus one could think that these two systems are essentially the same. But they are not. And before we do an explicit calculation that's going to show this, I'd like to present two rather intuitive explanations. First, I need to state that the net force for both systems is indeed 50 newtons. So we have a net force of 50 newtons here, and we have a net force of 50 newtons here. The downward force acting on the 10 kilo mass on the table is countered by an equal upward force exerted by the table. So the net force for both systems comes from the outward force acting on the string in case 1, or the 5 kilo mass in case 2. But these forces need to accelerate total systems with very different mass. In case 1, the total mass, m1, and there is no m2, so the total mass is equal to m1, is just 10 kilograms, whereas in case 2, the total mass is the sum of m1 plus m2, which is 15 kilograms. So considering that force equals mass times acceleration, the acceleration in case 2 is actually lower. This can be made particularly obvious following an idea of Reddit user Physmatic, who suggested scaling up the downward force. The 10 kilogram block stays the same, but now instead consider a downward force of 10 kilonewton for case 1, and a mass of the second block of 1000 kilogram for case 2. Now in case 1 the acceleration will be huge. Neglecting friction, it will be 1000 meters per second squared. But in case 2 the acceleration can never be more than g. It will approach g if the mass on the table and the friction acting on it become negligible compared to this huge mass pulling down, but it can never exceed g, which is 10 meters per second squared. So although the force is also huge in case 2, nearly all of that force is needed to accelerate this mass, which also became huge. Whereas in case 1, this huge force accelerates the comparatively small mass m1, which leads to huge acceleration. Another user named J01T suggests looking at the tension in the string, which is also a great idea. In case 1, we pull at the string with 50 newtons and thus apply a tension of 50 newton to the string. In case 2, we would only get a tension of 50 newton in the string if the system were stationary. If we exert an extra force in order to keep the 10 kilogram block stationary, the tension in the string would be 50 newton indeed. But since the 10 kilogram block feels a net force to the right, that net force lowers the tension in the string. Now if that still doesn't completely satisfy you, let's do an explicit calculation. So let us first delete these blue numbers. And now let's look at the forces acting on each of these masses. So we already established that there's a downward force from the mass m1 on the table and an equal counteracting force that the table exerts on the mass. These are actually equal to 100 Newton, but they cancel each other. We do need that force, however, to compute the friction force. So the friction force acts in the direction opposite of the motion of this mass. So that's going to be to the left, and it's equal to 100 Newton times this friction coefficient, which is 0.2. So we get 20 Newton of friction acting to the left. Now the final force acting on the mass m1 comes from the tension in the string. So we just write Ft, and that stands for the force with which the string acts on the mass m1. If we go over to case 2, we have the same situation, so forces counteracting each other here. Then the very same friction force of 20 newtons, which I'll call F mu, and I should write F mu here as well. Then we have the tension in the string, which is again Ft. So the string pulls with Ft at the mass m1. And of course the string pulls with the same force at the mass m2, and this time the force is pointing upwards. The tension in the string is what keeps the mass m2 from falling to the ground as if it were completely free, because there's obviously also a gravitational force acting on the mass m2, and that's equal to 5 kilograms times g equals 10 meters per second squared, so that's 50 Newton. Which is the reason why you could think that these situations are the same, but they're actually different, as we're going to see right now. Now let's focus on case 2 for a moment. So these masses are going to accelerate, and mass 2 is going to accelerate downwards, and mass 1 is going to accelerate to the right. But the value of that acceleration, the scalar value, is going to be the same. So we can say A1 equals A2. Now what is A1? A1 is just given by the sum of all forces acting on the mass m1 divided by its mass. So we have Ft, because that's in the direction of acceleration, minus F mu, because that acts in the opposite direction, divided by m1. And that's equal to the acceleration of the mass m2, which is given by Fg, minus Ft, because Fg acts in the direction of the acceleration and Ft acts in the opposite direction, divided by m2. Now you can use this to get an explicit expression for the tension force Ft. So if you solve this last equation for the force Ft, what you get is Ft equals F mu m2 plus Fg m1 divided by m1 plus m2. And we can now insert this into one of these expressions, but it's also quite interesting to compute this tension force explicitly. And if you do that, it turns out to be equal to 40 Newton. Now using this result, we can compute the acceleration A1 or A2, which are the same, so let's just call this A instead. And what we get is Ft over m1, so that's 40 Newton over 10 kilograms, which gives 4, minus F mu over m1, which is 20 over 10, gives 2, so that's 2 meters per second squared. And that's the acceleration of both the mass m2 and m1, so m2 is obviously accelerating towards the bottom, and m1 is going to accelerate towards the right. Now let's look at case 1. We only have one mass, but this tension force Ft obviously appears in the whole string, and it's actually supplied by this downward force F equals 50 Newton, so that's actually the tension that we apply to the string. So we can write down the acceleration of mass 1, which again I'm just going to call A, as this net sum of forces divided by its mass again, so that's Ft in the direction of the acceleration minus F mu, because it's in the opposite direction, divided by m1. That's a very simple calculation. That's just 50 minus 20 equals 30 over 10, so that's just 3 meters per second squared. And that's actually a big difference. So these systems do not behave the same as each other. And you can even make this effect more extreme if you increase the mass m2 and consequently increase the downward force in case 1. And I think if one looks at the calculation like this, it's rather clear. But if you're just presented with the problem, it can be quite confusing. And as I said a few years ago, I was totally confused by this as well. But it's a great example of how one should not jump to conclusions too quickly, and how you should take your time and think things through. So I hope you liked this. Check out the original post on Reddit in the description if you want, and see you next time. Bye!